Thank you very much. During the preparation, I would like to thank Professor Sedmak for his invitation, which I accepted really with great pleasure, because after a few months I can be here again.
Pleasure is ours.
Yes, and to meet friends and present our results. To be honest, when we spoke about the topic of presentation, I didn't know about previous presentations that were given by colleagues from Debrecen. So this is a little bit similar. So let me introduce our long time at faculty results and research what we are going and now outgoing that we have offered to cooperation also with not only Belgrade, but maybe we can see also with Hungarian people. Thank you very much, Simon. Let me introduce myself a little bit. I am from Slovakia, from Technical University of Košice, but one of faculty of Technical University is in Prešov. It's situated in Prešov. They are really close cities, about 30 kilometers today by highway, so it's no problem to get there. Košice are the second biggest city in Slovakia, and Prešov is the third biggest city in Slovakia. Our faculty started to deal with additive manufacturing many years ago. That we started as a beginning, with structures that we could see today in previous presentation. Of course, inspiration came from nature. We can see beauty of the nature around us. When we stay there, it's really beautiful to be there. But if you look at it like scientists or like technicians, we could see how efficient is nature. Nothing is solid totally. Even our bodies, even everything, plants, animals have cellular structures that are really efficiently built to help not only with beauty, with light reflection, for example, with sound absorption, but also with mechanical properties so efficient. So this is inspiration that came many, many years ago to us. And of course, additive manufacturing enabled these possibilities because complex structures couldn't be produced very easily by conventional technologies. So this inspiration from nature could be reality thanks to additive manufacturing. Of course, these cellulars are everywhere, as I mentioned, in our bodies, and additive technologies, as already been mentioned, with implants, could be implemented also in hip prostheses and so on and so on. Some implants not only for teeth, but for other properties that could be much more better treated after some insurance and so on. Is that additive technologies can help human in this way from the healthcare point of view. Of course, if we have some lightweight structures, it can help. It can be implemented in many devices that are very heavy for example, older people. So we can make them lighter to be more movable for older people who are not so strong as young people, and so on and so on. And if we look from technical point of view, lightning can be very useful also for not only automotive industry, but also aerospace, aircraft industry, because some studies found out that 1 kilogram saving of 300 tons aircraft can save about, I don't know, 17,000 euros. And in per year, 5 kilograms, for example, for long trip air flights can be even up to 1 million euros. It's one plane. How many planes do you have around? And this saving can help also for secondary way, because not only saving material, of course, it's saving fuel, and saving fuel means that we can save our environment, pollution, and so on and so on. Using this lightweight, because we started use plastic because of their properties that are light. We can, my mom can heavy milk or glass or bottle daily, 2 liters of milk with hands coming and so on. After that, we used plastic bottles to not so heavy bottles like glasses. And we started to use in amount, big amount portion everywhere. And what with this plastic we should do now? They are everywhere in micro plastic, micro particles in water, in our feet, and so on. So it's problem for next generations that could, we have a lot of allergies, children allergies, and so we should avoid this as possible, and we can use lightweight materials that are much more better recycled and used again and again. So if it is so, we can maybe be part of some improvements in next generation life. So of course, the next application could be for heat exchanger, for complex part of wings or turbines, for some crash energy absorption parts of cars, and so on and so on. This is ideas that we have started to do and to work on that, because we developed cooperation from our faculty with many universities that you could see, or some other organization through Europe at this moment. Hopefully we will go further. And of course, Belgrade is great potential help that could be. We have already started cooperation with Croatia. And last time also we were in Maribor with Professor Gubeliak and so on. We are now open for development of these challenges, as you mentioned, previous conferences, because we went through many these problems. As I very fastly show you that we started with as cheap as possible available technologies that was maybe 20 years ago, 15 years ago, with 3D printing of basic lattice body-centered cubic lattice structures. And we also could see how they behavior, and we could identify that this previously set up numerical analysis are not very well correlated with this type of bodies, could be said. So also we could see that damage and fracture could be in diagonal way, as you mentioned, or with different volume fraction concentric way. So it's something that could be also somehow be taken into account when some evaluation come. After that, we went through some correlation of frequency analysis, natural frequency analysis, model analysis with these basic simple structures. Last time we presented in Belgrade in November common paper based on this tensile tests. There were problems previously when we built samples that they were, do I have any pointer? That they were fractured in this way where the structure is connected with these parts and parts for tensile test. We solve it with strengthen this surrounding parts a little bit, and after that, these cracks should be much better positioned inside the samples. So results come with mechanical properties of this structure. We compared them with whole, solid material, and so on. We went through bending tests. Firstly, we produced these structures. We could see that technology is very, very important because pure tube had much more better properties in bending, like strengthened with this lattice structure. It was because problem of technology of this movement of nozzle with strategy of this printing and so on. So technology plays a big role with the properties, mechanical properties, of course, materials and topology, of course, but firstly, technology should be solved. Not only mechanical properties, but other properties, as I mentioned. We also already done a comparative study with these different types of structures with some absorption properties that can be used for many applications, from buildings up to some walls next to the roads, next to highways, up to other isolant between some spaces, or for good absorption or reflection properties in some operas, theaters, and so on. So this comparative study continues now. Our article is now directly under publishing this time, that we continue with other types of topologies, could be said, with trying to find how barriers and heights of the structure can affect the results of sound absorption properties. So after seeing this technology and problem with sharp corners, as we mentioned previous presentation, we found out that there are some type of structures that are complex structures, and they are so-called triply periodic minimal surfaces. They are smoothly designed, not with like lattice with sharp corners and so on. And we try to use this. What is the main advantage of these structures is also that they are self-supported. So they can be given inside some solids without necessity to have support structure as they are building. We started with materials with carbon fiber reinforcement PLA material, and you can see, not very well, maybe visible. I'm sure I can take it. Just how to say, technology again played a big role. We improved from this first attempt to this attempt with a PhD student that could be really nicely printed structure, so-called gyroid. Maybe you have already heard about that, but much more better properties with many other tests and experiments could be seen in diamond, so-called structure. I will show you the basic cell a little bit later. So we went through bending in comparative study, and you can see that in all cases diamond structure has the best properties as for this comparative study. Okay. We continued this project, and we had the opportunity to have production of inconel material or metal materials. We selected inconel as one of the best. Thank you. Bye. Have a nice trip. Okay. So we selected inconel as also potential material for 3D printing. Also, model analysis properties has been correlated with numerical analysis. Again, properties, compression and tensile tests were selected. So you can see here, we also try to combine these two most famous cells, like with these triple periodic minimal surfaces, gyroid and diamond, and we try to find what is the best. It's thickness or volume fraction. Thickness, wall thickness is important more, or volume fraction. So we can advise that thickness of the wall is much more important. So it should be evaluated based on that, because at the same volume fraction, this wall thickness plays a big role. So this is combination of two structures inside one model. And with inconel, we continue with smaller sampling compression test. Still, diamond had the best properties structure. There are many other different structures. We also used Neovius that is evaluated like the most close cell to the bone cells inside the bones. So we try to do that. And now we are trying to run analysis numerical. It's not easy to, because it's created within the software like a surface. It's not solid. So it's like surface, and it's necessary. It's not problem to have a STL5 for production, but for meshing and for elements, it's a challenge for us now to do that in the way so that the results of numerical analysis could be correlated with also experimental analysis. So we hopefully solve this problem for meshing now and trying to find the best boundary conditions to correlate all the results. And after everything still inconel, we went through aluminum alloy because of application of aerospace and aviation industry. There is very popular material for that. So this is also Neovius structure for bending tabs with also compression test, where we compare also how it's influenced by compression rate. If it is any influence is visible, it doesn't, this hypothesis was not confirmed. There is a very small, at this, the tested 3 rates, very small difference between that. And we again started to have a simulation and numerical analysis for compression to correlate. So this is not like typical scientific research result presentation. So instead of conclusion, I selected to show you what we are now working, and that is that has not been published yet. One test we are slowly going to fatigue test because it's live. It's not about just static test, but fatigue is really very, very important for applications. And this is from stainless steel, produced diamond type of structures that you can see preliminary static test, and you can see how big deflection this type of structure can have, because they can adapt. This bending bottom part can be extended, and this part that is compressed can be dense, and this deflection is really big. It was stopped because of machine limitation. So it's static test from stainless steel is really nice. We will see what will be this fatigue test of this structure. This application is for pure nickel. Why pure nickel? Because we evaluated its like potential application for catalytic application inside the cars. So we work on pure nickel, maybe later also, because catalytics use covering with some metals that are like valuable, but different word is used for that. And we use differently printed porosity of this structure. So not only porosity because of structure itself, but also porosity for inside the structure, inside the material. And this application is being to be applied for inside the catalytic application and catalyzers of other devices. And then this idea is how big difference is about the skin, about the structure, because skin is usually used to connect. It's not mostly samples are not just based on structures. They need some skin to connect components to each other in many applications. So how big effect has a different type of struts inside the structure in combination with skin around the structure. So that we could implement, and now we can implement the structures inside complex types of different components in wings of planes, in turbines that are not symmetrically designed, because in numerical analysis we can use in many times symmetric constraints and so on. But in such a type of complex components, we cannot use it. And so we need to apply the whole component and to numerically and also experimentally test the components. Of course, last step is with optimization of the structure. We can make the most important part. There is stress concentration with a dense structure. After that can be other parts of the same component made with lighter structures and so on. There are challenges that we can exchange slowly or smoothly from one structure to another if necessary. So there are challenges is optimization. Of course, there are some topology software that we also use, that we have at faculty, but many times this topology software offer such solutions that they are not very suitable for application and still needs to be again and again tested. This is that we can control. This is what is the also big advantage, that we can control in advance and we can check in advance. And if we know the basic behavior, we can also predict the next future life or behavior of component. So let me hopefully not big time because I'm talkative. Thank you very much for your attention, and hopefully we will see cooperation.